What role does bandwidth play in electrical signal amplification? Have you ever wondered how sound systems can make music so clear, or how your phone can pick up signals from far away? A lot of that magic comes down to something called bandwidth. So, what exactly does bandwidth mean in the world of electrical signal amplification? Let's break it down. Bandwidth refers to the range of frequencies that an amplifier can handle effectively. Think of it as the playground where the amplifier can work its magic. It is the difference between the highest and lowest frequencies that the amplifier can boost without losing quality. This range is usually defined by the amplifier's frequency response, which tells us how well it performs at different frequencies. When we talk about bandwidth, we often mention the 3 decibel points or the half power points. This is where the output power drops to half of its maximum value. Within this range, the amplifier keeps its gain close to what we expect, usually staying within a margin that allows the output to remains at about 70% of the ideal value. Now, why does this matter? In fields like analog signal processing and control systems, bandwidth plays a huge role in how well signals are amplified. If the input signal has frequencies outside of the amplifier's bandwidth, those frequencies may get distorted or even lost. Imagine listening to your favorite song, but parts of it are missing because the amplifier couldn't handle those high notes. For example, in audio systems, if an amplifier has a narrow bandwidth, it may struggle to reproduce fast changes or high-frequency sounds. This can be a big deal in communication systems or when conditioning signals from sensors. From the perspective of electrical engineering, several factors influence an amplifier's bandwidth. These include the design of the amplifier, the number of poles in its transfer function, and any unwanted capacitances or inductances. These elements can create shifts in phase and changes in gain that limit how well the amplifier can perform across different frequencies. For operational amplifiers, the gain bandwidth product is a key specification. This tells us the frequency at which the amplifier's gain drops to 1. Designers need to ensure that the amplifier's bandwidth is wider than the signal bandwidth to keep the gain consistent across all necessary frequencies. In practical terms, when selecting or designing an amplifier for a specific application, bandwidth is a key consideration. In control systems, for instance, amplifiers must react quickly to changes in input, which requires a bandwidth that covers the frequencies of those control signals. In communication systems, amplifiers need to manage the entire frequency spectrum of the signals being transmitted to avoid any distortion. Sometimes, bandwidth limitations are intentionally set to filter out unwanted noise or to prevent instability at high frequencies. To sum it up, bandwidth is essential for determining how well an amplifier can boost signals without losing quality or introducing distortion. It is a fundamental aspect of electrical signal amplification that affects everything from sound clarity to system stability in analog signal processing and control systems. Understanding bandwidth helps us appreciate the technology behind the devices we use every day.